All right, good afternoon, everyone. Hope you guys had a good weekend. So we're going to probably finish up our discussion of the support vector classifier today and support vector machine. So let's just go back and review a little bit about what we were saying last week. So we have okay, let's start on this page. So when we talked about linear separability, we were able to write linear separability this way, which says there exists some B and W, so that for all training samples, this sign-corrected score is greater or equal to 1. And then we were able to combine that with our equation for the distance, the sign distance from a point to the boundary, to get here. So this is an important relationship. It says that if you look at those sign-corrected distances and you change the signs on them, so in the case you have linearly separable data, these will all be positive. And it says that this is a lower bound on essentially the distance from a point to the boundary. So here's a picture. So we have these points. This is a linearly separable data set. We can split the two kinds of labels with a line here. And this is the margin. This is a lower bound on the minimum distance. So you can see that all these points are at least this far from the boundary on either side. Okay, so we sometimes call this the street. This is like the half width of the street. And we said that we would like a classifier which gives us the widest street, because that would be the most robust. Because, for example, we could make a classifier like this, which is also linearly separating the data, but then it has not much room there, and perhaps a test sample will be over here and we would make a mistake. So we're looking to find the B and W, which determine that boundary, so that there's the biggest amount of space between the boundary and the data. So that's kind of the theme for this unit. And because that lower bound is 1 over the norm of the weights when the data is linearly separable, that led us to our first procedure, which is to minimize that norm, which maximizes 1 over the norm, subject to this linearly separable criteria. So if we solve this optimization problem, which is minimizing this subject to this inequality, this set of inequality constraints, we will be able to place this boundary just perfectly so that the minimum distance here is maximized. So that was our first attempt at this. And we said that the challenge with this, or the limitation of this, is that this requires the data to be linearly separable, which is not something that happens usually in practice. In practice, typically, the data sets are not linearly separable. So if you tried to use this, it would basically say, there's no solution, that's it. So that's not a very good approach. So we said, okay, let's take this inequality constraint, let's rewrite it in a slightly different way, and then let's replace this inequality constraint with a cost term that has a very similar form, except instead of saying this inequality must be satisfied for all I, it says I'm going to assign a cost and I'm going to sum it over all the I for which this fails this inequality. So by looking at the max of 0 or this term, this quantity will be 0 whenever this is not satisfied, or if this is satisfied, this quantity will be 0 and this extra cost will be 0. So this is sort of a way of switching from this hard constraint to the soft constraint. And when we do this, that inequality gets replaced by this. So here's the first term here, but then we need this constant c to balance things. So essentially, if this constant is large enough, what will happen, and if the data is linearly separable, what happens is it will drive this term to 0. And when this term is 0, that means that this is satisfied for all I. And if you do that, you will get exactly the same solution as this gives you. Okay, so whenever the data is linearly separable, this support vector classifier is doing exactly what we want. But the advantage is it doesn't need the data to be linearly separable. If the data is not linearly separable, that just means that this term will never go to 0. And so what this tunable hyperparameter does for us is allows us to trade off between how important this part is and how important this part is to minimize. So if you make C very large, it really does its best to try to enforce this as much as possible. On the other hand, if C is small, then it says, I don't care if this is violated a lot, that's fine. Instead, it's going to focus on making this small, which makes the street wide. So we've seen some pictures of this. So the first case, when C is very large, you get a very small street, and you find that if the data is linearly separable, there would be no points in the street. If the data is not linearly separable, there could be a few violations. Points in the street are on the wrong side of the street, but it's doing the best job that it can. On the other hand, if you make C quite small, then what happens is it makes that street really wide, and it lets there be a lot of points in the street. That's all these circles. And so neither of these are necessarily the right thing to do. They both have advantages and disadvantages. So when we look at this side, the advantage, we can say, is low bias, but the disadvantage is high variance. And this is because over here, essentially there's going to be a very few samples in your training data set which are going to determine what your B and W coefficients are, just the closest ones. And so if you imagine doing this experiment over and over with different randomly generated data sets, you would see that this boundary would change quite a bit from one experiment to the other. And that is an indication of high variance. It's akin to using a very small training data set. There's just a few points that are determining the solution. So, but on the other hand, it has low bias because it's really trying to minimize things like classification error. On the other hand, when you go to this side over here, you see that the street is extremely wide. And the good thing about that is that all these circled points are being used to determine where the boundary is. And if you imagine doing this experiment over and over again with different random data sets, what you would see is that this line would not really change very much from data set to data set because it's essentially doing some average of all those points. And that average is going to be pretty stable when the number of points is large. So over here we have a low variance solution. However, we have a high bias solution because now this design is not focusing on just the few closest points. It's focusing on trying to make the boundary good for all these points. And when you look closely at what's happening here, there's actually some of these points that are now misclassified. They were not misclassified over here, but they are now because it doesn't really care just about the points close to the boundary. It cares about all these points. Okay, so there's, on either extreme, it's probably not optimal. Here you probably have variance too high. Here you probably have bias too high. There's some point in the middle that is probably optimal, and you can find that by doing cross-validation. K-fold cross-validation, a grid of different C values, just the same thing you've done with Lasso, with Ridge, with many of your designs before. Same procedure. And you can eventually find the C that's going to have the best trade-off between bias and variance. Okay, so that's what we talked about there. Any questions on that? Okay. Then to understand this better, we compared it to logistic regression, and we wrote them in the same way, and we noticed that they differ only in this term that is applied to each of the data samples. And in the case of the SVC, you have this very simple, sharp curve here that's called hinge loss, whereas with logistic, you have this nice smooth curve that is logistic loss. And essentially, what's special about hinge loss is that it goes exactly to 0. Over here, that means that all the points which have z greater than 1 or yizi greater than 1 are going to essentially be ignored by this design. It's only going to focus on the ones causing the violations, which are those. Logistic loss, you can see that it uses all the points. This never goes to 0. It just gets smaller, but it never goes to 0. Okay, so it's another way of understanding SVC in terms of the loss. And then we tried to do something which will be a little bit useful today, but what we tried to do is we tried to do a gradient analysis of this. We tried to take derivatives with respect to b and the gradient with respect to w. We tried to set them to 0, and we found that this gave a bit of insight, but the lack of differentiability of that hinge loss prevents us from actually deriving what the gradient and this derivative are for a few of the points, the ones that are right on the edge of the street. And so that was, this is sort of not a successful analysis attempt. But as we'll see today, these equations will actually come back in a different form. That's part of why we're doing it. And I think the last thing we did was we said that sometimes the SVC is written in a slightly different way, where what you have are slack variables. The slack variables, these xi's, they measure essentially how much violation of the margin you have. So for any points that are on the outside the street and on the correct side of the street, they would have the slack variables equal to 0. If you're on the correct side of the street, but on the edge of the street, that's also 0. But what happens is as you get into the street, the slack variable increases. Eventually, once you get to the boundary, it becomes 1. Once you get to the wrong side of the edge of the edge of the street on the wrong side, it becomes 2. And once you keep going, it just gets larger and larger. So it's just a different way of writing the SVC that you might see in some other sources, like the Wikipedia page. Okay, and that brings us to where we are now, which is what do we do when we have more than 2 classes? So we know for any kind of linear classification, our approach is as follows. We build a separate prediction, vector of prediction weights for the problem of, so this first one says, B and W say, are you in class 1 or not in class 1? The second pair says, are you in class 2 or not in class 2? All the way to, are you in class capital K or not? You also get a vector of scores. And that's basically how we do multi-class linear classification. So the key question now that remains is, how do we train B and W? And we talked about this for logistic regression. In that case, we said that there's 2 options. One option was the one versus rest approach, and we have that same approach here for SVCs. So in that case, you design, let's say, the B1, W1 pair separately from all the other ones, and you design it as if you were doing a binary SVC. So it's like you repartition your data into class 1 and not. Now you have a binary data set. You can solve that problem. And now you get your B1 and W1. Now you say, what's B2 and W2? You repartition your data into class 2 and all the others. You have another binary problem, and so on. So that's one option. Separately train these one versus rest binary support vector classifiers. There's another option, which is to jointly train all the weights and biases using this Kromer-Singer approach. So this is analogous to the multinomial logistic regression we learned about in the last unit, which was also a joint design, but this one is taking this SVC type approach versus the logistic approach. So when you look at this, this is the cost function. It looks a little bit complicated. So this is the part that got replaced. This used to be the hinge loss, and now it's more complicated because we have more than 2 classes. Everything else is pretty much the same. This is the Frobenius norm. This is just the sum of the squares on the W's, so that's the same. So this is the new part. And although this part is maybe a little bit unintuitive, if you go through the analysis and you say, well, what happens when there's exactly k equals 2 classes? So even though usually in that case, we formulate the problem with a single weight and a single bias, you could imagine formulating it this way where you have 2 scores, 2 biases, and 2 weight vectors. And you could apply this approach. And it turns out if you do that, down here there's a little analysis that shows you eventually get exactly the same formulation as the binary SVC. So the point is that this really is a direct extension of that, even though it might look a little strange. It's just a direct extension of that idea to multiple classes, or more than 2 classes, possibly more than 2. So, so it's going to be a little bit more expensive computationally than designing them separately, but it's going to work a little bit better in most cases. Okay, so that's all I have on all the mathematical details about the SVCs. Are there any questions before we move on to some of the practical things like how you work with scikit-learn? Okay, great. So this is how we do it in scikit-learn. Not surprisingly, it's very similar to how we interface with other predictors like logistic regression or linear regression and so on. In this case, you would use this linear SVC. That is that's the method. But there's a few interesting choices we're going to make. So here, this is taken from the demo, and in the demo, we're doing MNIST, which has 10 classes. So we have to choose how we're going to do the multi-class aspect. So we can do Kramer-Singer, as we have here, or we could do one versus the rest. That's essentially the other option. So here in the demo, I'm choosing the Kramer-Singer approach. There's another interesting thing, which is the loss. So even though when we talked about the loss of the SVC being hinge loss, interestingly, by default, scikit-learn uses squared hinge loss, not hinge loss. So let's try to think about why that is. Let's come back to this picture. So here's our picture of hinge loss. And what I'm saying is they use the square of this. So what is that? Can you visualize what that looks like if you square that? It's like this, right? So it's a parabola or half parabola. So any idea why it would do that by default?
Might make it easier to differentiate at the point.
Exactly. It's differentiable. So it turns out for these optimization algorithms, they run a lot faster when the cost function is differentiable. So this non-differentiability here, yes, it's a convex problem. We can solve it with an algorithm, but that algorithm runs slower because it has to deal with this non-differentiability. So when you square it, you get a nice differentiable term, and you can solve it faster. In my experience, however, the performance goes down. So it's a trade-off. And for the lab, or the demo, I decided to use the traditional non-squared hinge, which I had to specify this way. And I found that gave a little bit better performance. Other than that, you have to specify the value of C. Remember, that's going to be a trade-off, bias variance sort of trade-off. And when you do all this, and everything else is just like you would imagine, you do dot fit, you do dot predict, you can compute the accuracy the same way, and we get an accuracy of 90.7%, which is about 0.5% better than logistic regression. Yes?
Why did they square it if the performance is worse?
Because it's faster. So it's always a performance computation trade-off. So in my experience, all the times I've tried it, I find the performance to be a little bit worse. I don't know that that's universally true, but that's just my experience. But I also see that it's a lot faster to optimize. So like a lot of numerical methods, there's a trade-off between speed and accuracy. So I don't know who chose the default at scikit-learn, but someone chose that to be the default. Of course, we have the option, to change it and try both.
When you say performance, you mean accuracy?
Yes,
Okay.
sorry, yeah, the accuracy got worse, the speed got faster. So sorry if I was unclear about that.
So, so you said the accuracy got worse and the speed got faster. So let's say that is one possibility, but why not, use more time and have better accuracy?
It's always a trade-off. So, sometimes, depending on your data set size, if the data set is big enough, it may just be infeasible to wait that long. It might be the difference between like being able to solve the problem or not. So, there's always a trade-off. That's kind of, when you eventually graduate from here and they pay you the big bucks, they're paying you to make smart choices on things like this, to understand them, understand what the options are, the costs, the trade-offs, and to make a good choice. Yeah. Okay. All right, so we spent a lot of time doing all this math in this unit. Is anyone a little bit disappointed that the performance is only 0.5% better? It's like, was this whole thing worth it? All this effort, right? Maybe not, right? So it turns out this is not the end of the story. And this performance, if you remember, back at the beginning, I showed you a table, and in that table, the support vector machine, it was called, was actually, much closer to, I don't know, it's maybe 98% accuracy or something, not 90 or 91. So this is not the end of the story. We've just kind of done the first part of the story. And so now we're going to move on to give you the second half, which is basically building on what we've done, but just adding one important new trick, or maybe two important new tricks. So this thing we've talked about, we're going to call it the support vector classifier. This works very well when the features are nearly linearly separable. So for some data sets, that's going to be true. For some data sets, it's not going to be true. To try to make the features more linearly separable, we can rely on our old trick of let's do some sort of nonlinear pre-processing on the raw features. We've been doing this kind of stuff all the way back since, I think, Unit 1, where we said, like, let's, instead of predicting miles per gallon, let's predict inverse miles per gallon. Or when we talked about polynomials, we said, let's square the features, let's cube them, let's, and so on and so on. So in general, if you can find a good nonlinear transformation to make your data easier to work with, your accuracy of prediction might go way up. So that's the idea, is to do some sort of feature transformation. And in this unit, we're going to denote this feature transformation by this function phi. So these are going to be our raw features, and phi of x are going to be our preprocessed or transformed features. And this little arrow just means like you're basically replacing x with those. So instead of using x, let's use these new features. And so here's just an example, kind of just a drawing, but I'll show you a slightly more realistic example. So in this original space, you can see that there's no way we can linearly separate the red from the blue. It's just impossible. However, maybe there's some kind of nonlinear transformation, and often the transformation is to a larger, higher dimensional space. We're going here from 2 dimensions to 3, and in this new 3-dimensional representation, it is possible to pass a plane to cleanly separate our data into the two classes. So this is kind of the spirit of what we're trying to do. Use a feature transformation that typically will increase the dimensionality, but will give us data that is easier to separate. And to deal with the extra computational burden of working in this higher dimensional space, we're going to do something called the kernel trick, which is going to avoid all of those issues. So those are the sort of two pieces to this thing, which we'll call the support vector machine, which just takes the SVC, but adds these two new things to it. So let me show you another example of this. It's still a toy example, but at least it's real. So let's say that this is our original data. It's hard to see the colors here, but there are blue points here and red points here. So there's clearly no way I could use, in this raw feature space, I cannot build a linear classifier, right? A line. I can't split these apart with a line and perfectly separate the red from the blue. However, what if so this is my original raw features x1, x2. What if I do this pretty simple transformation where what I do is I keep those two raw features, but then I add a third feature, which is the first squared plus the second squared. And so now I've gone from 2 to 3 dimensions. So now these are my new features. And essentially, I've kept these axes the same. I've just added a new feature, this. And now you can see that because the data here, this would be the origin, that as you go farther from the origin in any direction, this new feature increases. And now the red are very well separated from the blue. We could pass a plane through here, and we could cleanly separate them. Okay, so again, this is a toy. This is not really what happens with real data, but it's kind of to just illustrate that maybe it could happen, or if we can somehow find a good fee, then maybe we can have that happen. So that's the goal. Okay, so all right, any questions? Is this making sense? Okay, so this is how we would do it. This is our support vector classifier. And the only thing we need to change is how we construct the score z. So previously, we had W transpose xi. So all I'm changing now is instead of using xi, I'm using phi xi. Okay. And so let's say I do this. Now I have a new optimization problem. It's not really, in terms of the weights, the W and the B, I haven't changed anything about the problem. So the problem can still be solved in exactly the same way. If we could solve it before without the phi, we can solve it this way. It turns out that this is a convex problem, so it's solvable with an algorithm. And so we can get the optimal weight and an intercept term. Once we have them, this was the equation that we said governs how you come up with the prediction of a test feature. So here we have, these are the training quantities. This is the test quantity. And here I'm writing this in terms of these alpha i's. The alpha i's are, okay, it's not exactly obvious how they're related to these, but here I'm referencing that where was it? This derivation we did here, where the weight vector is going to be some function of these things for some coefficients alpha I. We weren't able to figure them out this way, but you can figure out what they are. And so the point here is just to say that the only extension we need over here is we just need to stick in the fees in those two places. Okay, so it's definitely possible to do this if we have a phi function. It's a small change to our support vector classifier to use it. Now, I'm saying that this is what you could do in principle because this is not what we're going to do. And the reason why is, what if the dimension of our new features are very high? So what if we have expanded the dimension, by a huge amount? So where you'll see the effect of that is now this W vector needs to be much larger, right? Much longer. You have way more coefficients here, and so that means that this optimization problem is going to be a lot harder to solve. So so that's sort of the downside to this. And now it might be strange to say, what if I want to use an infinite dimensional phi? So it takes us from a finite number of features, and somehow maps us to this infinite dimensional space. Now you might say, why are we even talking about this? Like, who does that? Right? Well, it turns out that the most popular phi function, as we'll discuss in just a moment, actually does this. It's called the radial basis function. It does this. Essentially, it's implementing what would be like an infinite dimensional phi. And so if you approach the problem in this way, that would mean you would need an infinite dimensional W, like an infinite number of weights, and that's just simply impossible. You can't design it, right, with a finite computer. So, we basically can't use this equation directly. We need to think about a slightly different way of solving our SVC that will allow us to bypass this problem. So that's the goal. And this is what it looks like. So I apologize that the derivation for this is outside of this course. I can't explain why this ends up looking this way. If you're curious, you can go read section 12.2 of this textbook. This is one of the textbooks that was the recommended optional reading. But basically, it's saying, okay, don't solve for the weights and the B. Instead, solve for these lambdas. And so this is the optimization problem we want to solve. So here is minimize this cost subject to lambda I must be in the interval. Each of the lambdas must be between 0 and C. It's the same C we're used to dealing with. And there should be this equality constraint as well. It turns out that this is a convex optimization problem, so it can be solved. But what you see here is that you are never directly computing the W vector, right? You're just avoiding that entirely. And so this is how we're going to escape the fact that this might grow to a dimension that's too high or infinite. So this thing is called Lagrangian dual form of the SBC. So it's sort of like, it's just a different way to formulate this optimization problem. If you guys have studied convex optimization, you would have seen this before. So it's just sort of a way of turning the problem around and designing some other parameters that we're going to call them lambdas, and they essentially just solve the problem in a different way. So now if you wanted to, you could, once you're done solving for these lambdas, you could compute the weight and the intercept, but you don't actually need to, because the lambdas give you everything you need to compute the labels, the label predictions. So here we're using the lambdas, we're using our test vector x and our training samples. We do need this bias coefficient, and it turns out that is computable again using the lambdas. So basically, we don't ever have to compute the W. There's a way around it. And when you do it this way, the dimension of the lambdas, by the way, this lambda vector is n, which is the number of samples in your data set. So that's always going to be finite, right? So you're sort of, instead of solving it in this d-dimensional space, number of features, you're solving it in this n-dimensional space, number of samples. Okay, so again, I don't have a good explanation for this. However, I do want to point out a few things that might look familiar. So if this is an equation that we saw before, so the idea is, okay, if you look at these equations and you plug in, every time you see a lambda, you plug in C times alpha I, then you end up getting those equations that we got from the gradient analysis. So you end up getting this. This is something we saw before, where lambda was CAI. This was something you saw before. I think this must be 2. And yeah, so basically, that was part of the reason for going through those, to give a little bit of intuition as to where some of these things are coming from. But okay, so let's say you believe me that this is another way to solve the SVC. So now the question is, well, how do I modify this if I want to use these transformations like phi? So essentially, wherever you see the x, we just have to replace that with phi of x. And when we do that, Here I highlighted them in red. So these are all replacements of x with phi of x. And the difference, notice that in some cases we have the training sample, the test sample, the training sample, a particular training sample. So the xi is any I that corresponds to a support vector in our training set. Here we have like xi, xj, and so on. And this is the new problem that we would need to solve with the transformation. And now the interesting thing is, whenever the phi appears, it actually appears in this phi transpose phi form. So it never appears on its own. And if I just give this phi transpose phi a different name, I'll call it kappa. And kappa takes in two different versions of x. We'll call it x and x prime. You know, so like here would be xi x, or here would be xi star, or xi xj. Basically, think of this as kappa, kappa, kappa. And now this says, okay, let's not design a phi explicitly that might have massively high dimension. Let's just design kappas. These things are called kernel functions. Let's think of kappa directly. And the whole point is that directly computing kappa is easier than computing the individual transformations and then taking their inner product like you have here. So this is called the kernel trick. And if you do this, you bypass the need to ever explicitly define phi or work in a very high dimensional, possibly infinite dimensional space. So this is how the support vector machine comes about. I'm explaining it from the perspective of feature transformation, but at the end of the day, we never actually build an explicit feature transformation. The thing we build explicitly is the kernel. And a kernel, you could say, is a way of measuring the angle or the inner product between two different feature vectors. So this thing is called the kernel trick. So let me show you what a few of these kernels look like. So the most popular one is the radial basis function kernel. It's kind of intuitive, actually. You take the difference between x and x prime. You just look at the 2 norm of the difference, and then you exponentiate it. You have exponential of minus lambda times that. So if you remember how this exponentiation sort of works. So, okay, if the difference is exactly 0, right, then it's e to the power 0, which is what? 1, right? So that's the largest it can be because of this minus sign. As these x's get farther apart in a Euclidean sense, their distance, their squared norm actually gets magnified by this e minus gamma. Because remember that this e minus gamma basically falls off very quickly, goes to 0 very quickly. So when you have points that are pretty close together, this is large, maybe somewhat close to 1. But as those points get further apart in Euclidean distance, this vanishes very quickly. It's basically defining what you could say is a local neighborhood. It's like if 2 points are close enough, you consider them neighbors. And at some point, when they get a little bit further away, you say, nope, they're no longer neighbors. There's essentially no connection between them. That's kind of what this kernel function does for you. So it allows you to figure out which points are close together and any other points that are not close to them. It just says they're not neighbors. So that's one way to do it. There's other ways to do it. Instead of using an exponential here on the square difference, you can use a polynomial on the inner product. That's this polynomial transformation. So here you have to choose what power d you're going to use. You could use a sigmoid. We didn't talk about it, but a sigmoid and a hyperbolic tangent are very similar. You could use a sigmoidal type shape. Or you could use no kernel at all, which is essentially what we're doing with the SVC. That would correspond to kappa is just, x transpose x prime. So as we know, this is not very powerful, but it's sort of a bridge between what we're doing now and what we were doing earlier in the lecture. So this is essentially no or trivial transformation. Okay, and the key thing here is intuitively, each of these kernels measures some form of similarity between its two inputs. So when the two inputs are similar in some sense, in this case it would be close together in Euclidean sense, the kernel is large. As they get further apart, the kernel goes very quickly to 0. And they all have a slightly different definitions of that similarity. Okay, so that's essentially what we're doing here. So just to recap, we started with the SVC, and we said we would like to do some nonlinear feature transformation, maybe to a higher dimension. We said, okay, we could do that in principle. The trouble is that forces us to work with an equally high dimension W, and that means that this optimization problem might get too difficult to solve. So we said, let's, instead of computing W and B and then using them here, let us use this other approach, Lagrangian dual, which avoids ever computing W and B. It computes these lambdas, and the lambdas are all we need to do our classification. And if we do that, and we plug in our feature transformation, then those phi functions never appear on their own. They're always coupled together with another phi. And then we said, great, let's never even talk about the phis anymore. Let's just replace them with kappa. And so this will be a kappa, this will be a kappa, this will be a kappa. And now let's just come up with a good kappa that is going to work well for us. And when we do that, we never have to work in this super high dimensional space. We design a vector of dimension n, where n is the number of our data points. We never have to worry about the dimensionality of our transformed features. And we saw a few kernels here. So it's a good place to pause and answer questions, talk about this. Yes?
Is it possible that we get the fees, but it look like?
So the fees, like to visualize the fees is quite hard. Like we saw one example in 3 dimensions, but as humans, it's hard to visualize more than 3 dimensions, right? So this is this is one example of a fee, but it's hard to picture like realistic fees and visualize them.
So we're just making those covers instead of fees.
Yes, we're not even going to make the fees. We're going to make these kernels kappa, and the kernel kind of is just a way of defining similarity between 2 feature vectors. Right.
Can you go back to the slide 30?
Yeah.
Yeah. So our final equations are going to be the 3 that are on this page, just with the phis in red replaced with the kappa.
Yes, we're going to have we're going to have that kappa. We're going to have this be a kappa, xi star, and this would be kappa xi xj.
Is the star here still like a hat in the previous slides?
So so this is going to be, so like this b star is given by this equation, and in this equation, the I star is any support vector index. So you can choose any of your, so this is I is the index into our data set. Just choose one of the ones that was used to design, that's a support vector. So that was, I think that was given on this page somewhere. Or maybe it was on a previous one. But yeah, that's what the xi star is.
Is there a unique feature transformation for every kernel?
That's a good question. I mean, I guess no, because like here I could change the sign on phi, and you would not be able to tell from this, right? So you can imagine other things you wouldn't be able to see. Yeah. Like, in fact, you could change the sign randomly on every element in this vector, and you would not be able to see it from this.
So I guess in that case, it would be difficult to derive a feature transformation from a kernel.
Yes,
Okay.
that's right. You go from the feature transformation to the kernel, but not backwards. Yeah. Okay, some other questions? Yeah.
Are you going to determine what kernel they use as an application?
That's a great question. How do we know which kernel to use? So I would say that that's kind of the biggest downfall of these methods, is it's not always going to be clear. The one that seems to work best out of the typical kernels is this RBF. This is kind of like the default one most people use. But I'm sure there's going to be some applications where, you know, maybe this doesn't work as well as you'd like, and you might try to do better. Maybe you're going to try to design your own kernel. In fact, on previous versions of this course, on the final project, I had students like coming up with different kernels, and they were actually outperforming this one on the data set in the project. So that's definitely something you can do. But it's also the main motivation for what we're going to do next, which is to try to design a fee, to try to learn a fee from the data itself. Okay, so that's where we're going. So I'm glad you asked that, because that's kind of the whole limitation here is, yeah, this works pretty well. We'll see that it actually works quite well, but it's not always clear, yeah, which one to use. Basically, you just got to try them, and then, you know, if none of them work very well, you might try some modifications, but it's not very satisfying. It feels pretty heuristic. People have done a lot of analysis of these things, so I mean, there's theory about how well they work and so on and so on. But yeah, it's like you're not really designing the kernel based on the data set you're working with, and that's what we would ideally want to do.
Previously, we see that the phi is infinite in dimension, but where does the notion come from? Because we didn't even know what the phi is.
Yeah, so, okay, that's also a great lead in to what I'm trying to convince you down here. So if you try to figure out what the phi function could be for the radial basis function kernel, again, we don't exactly, you know, there's no way to get it exactly, but one thing you could do is you could use this series expansion of the exponential, and you could write it this way. And here you have an infinite summation of terms where you have this raised to different powers j. Okay, so this is kind of like an indication that if you did try to find a phi that would work for this RBF, you could never do it perfectly with finite number of dimensions, because essentially you're trying to approximate this infinite dimensional sum, and you just need like an infinite number of coefficients in phi to do that. So yeah, we don't know exactly what it would be, but we do know that for the RBF it would be infinite dimensional if we could build one. So that's again what I was saying. Like the most popular one essentially has implicitly uses a feature transformation that's infinite dimensional, but explicitly we never actually transform the features. We solve this Lagrangian dual with that kernel. Okay, great. So those are great questions. Any other questions? Okay, so let's see how we implement it. So in this case, in scikit-learn, we use svm.svc. So if you remember the previous one, it was svm.linear svc. This one doesn't have that linear word in there. So for this one, you can choose from several kernels, the ones I listed on the previous page, or you could build your own kernel. You just define a function of two vectors, give it to that. You have to specify the kernel width, so that's an important tuning parameter. So that's this gamma here. So all these have a kernel width, which essentially it sort of defines that local neighborhood. It says, you know, how far away do 2 points need to be for them to not be considered neighbors. So that will greatly affect how this thing behaves. And then in some cases, you can see there's other tuning parameters. You know, here you have to choose D, R, and gamma, and so on. But for the radial basis function, there's two. There's gamma, and then there's the C. C is, remember, that's the same weighting we talked about before. That's controls like a bias variance trade-off. Okay, so those are the things we got to do. Tune, and we would tune them with cross-validation, just like before, except now we'd have to do this two-dimensional cross-validation, which takes longer, so it's kind of a pain. But that's essentially it. So here's like SVC. You can tell it whether you want it to return some soft outputs or not. By default, it doesn't. It's a little bit faster if it doesn't have to compute some soft outputs. Tell it which kernel you want, the values of C and gamma. And that's essentially it. Then you do your dot fit, your dot predict, and so on. And here we see we went from 90.7 to 97.1. So this is a huge leap in performance. This is really, finally we have the payoff we were hoping for, a massive jump over the traditional linear method. So, should we consider this to be a linear classifier or not? Sort of a, I don't know. In some sense, it's definitely not linear in the raw features X because they are getting transformed by this, the kernel is essentially doing some implicit nonlinear transformation. On the other hand, it looks a lot like other linear method. So, whether we call it linear or not is kind of a question. It would be linear in that transformed feature space, but not in the original raw space. Okay, so that's essentially the implementation. Well, we're almost done. Just one more slide. So things get a little bit complicated when you start talking about multiple classes and what scikit-learn can do for you. So this slide just goes through all the different things. So let's say you want to do one versus rest to attack this multiple class problem. So we know that means for each class K, separately train a binary one versus rest classifier. So the only way to do this in sklearn is to actually use the linear SVC method, not this new one, not this new SVM. The trouble with that linear SVC method is it only works for that linear kernel. It cannot use an RBF polynomial or whatever. It's just the simplest linear kernel. So that's the one versus rest option. We talked about the Kramer-Singer option, which is one way to jointly train this classifier. And this is also implemented in that linear SVC only for the linear kernel. So again, that's not really, okay, maybe it gives a slight boost over one versus rest, but it's not massively better and it's slower. And so how does the SVM work now, this one we just talked about? So it turns out that it uses this one versus one thing, which we talked about this back in Unit 5. So in that case, for one versus one, for each unique class pair, you separately train a binary classifier. So for example, if we had 4 classes, so one way to make, well, maybe I'll do it with three classes. So you have a class pair like 1 versus 2. You could design a classifier for that. You could design a classifier 1 versus 3, and you could design another classifier 2 versus 3. So those are each class pairs, and there's going to be k times k minus 1 over 2 class pairs. So that is what's implemented in SVM SVC, and in this case you can use a variety of kernels, like we can essentially do the SVM we just talked about. Generally speaking, it's going to be slower than the linear SVC. but it's the only option if we really want to use one of these fancy kernels like RBF. Well, I should say it's not exactly the only option. There is a variation on it. It's not really very different. You could say that the interface is slightly different. The only difference in this thing called the new SVC is that instead of using C, which is a real number that could span many orders of magnitude, we don't really know how to choose it, it instead uses a parameter new that's between 0 and 1, and it's interpretable. New is a lower bound on the fraction of support vectors. So if you set new as 0.5, you know that at least half your data samples will be used as support vectors. And so this way, it's just a bit more interpretable than this number C, which C could be like 100 or 0.01. We just don't even know. But new, it's just a bit more interpretable. So other than that, it's very similar. So you might prefer to use new SVC just because it's more interpretable. Performance would be the same. You could eventually find some new and some C that work exactly the same way. Okay, so that's all I have for this unit. It's a good time to stop. Any last questions? Okay, so next time we'll get into this question of how do we learn a transformation that is for the data set we're working with. And that is when we're going to start talking about neural networks, because that's exactly what they do. So it's an exciting time in terms of the material, and we'll continue this discussion on Wednesday. See you guys then.